How does a feedback signal work in feedback control? Have you ever wondered how systems maintain their performance and accuracy? The answer lies in feedback control. Let's break down how a feedback signal operates in this context. In a feedback control system, a feedback signal is a part of the system's output that is sent back to the input. This creates an error signal, which is the difference between what we want, known as the reference input, and what we actually get as output. The controller uses this error signal to adjust the system input, aiming to minimize the error and align the output with the desired value. This forms a closed-loop system that continuously monitors and corrects itself. In electrical engineering, feedback control works by sampling the output signal and routing it back to the input through a feedback path. The feedback signal is compared with the reference input at an error detector. This detector calculates the error, which the controller then processes to determine the necessary adjustments to the input. This adjustment influences the system's output, steering it toward the target value. There are two main types of feedback: negative feedback and positive feedback. Negative feedback occurs when the feedback signal is inverted compared to the input. This helps stabilize the system by reducing the error. It enhances system stability, accuracy, and bandwidth while minimizing sensitivity to changes and noise. You'll often find negative feedback in amplifiers and control systems to maintain consistent output even with disturbances. On the other hand, positive feedback happens when the feedback signal aligns with the input. This can increase the system gain and may lead to oscillations or instability. Positive feedback is intentionally used in oscillators and multivibrator circuits to generate sustained signals. The feedback loop consists of several key components. First, there is the reference input, which is the desired output value. Next, the error detector compares the feedback signal with this reference input, producing the error signal. The controller processes this error signal to decide how to adjust the input. The plant or system is the process being controlled, and the feedback path is the route through which the output signal is sampled and sent back. In practical applications, feedback control is vital for maintaining stability and performance. For instance, in amplifier circuits, negative feedback reduces distortion and manages gain. In motor speed control, feedback from sensors adjusts the input voltage or current to keep a constant speed, even when the load changes. Engineers also use frequency compensation techniques, like Bode plots and Nyquist stability criteria, to design stable feedback loops by analyzing gain and phase margins. Overall, the feedback signal plays a key role by providing real-time information about the system output back to the input side. This enables continuous correction and control, helping achieve the desired behavior of the system.